Okay, so today we're going to look at area and Riemann sums, particularly the idea of how we find area underneath a curve. So let's say we have this function here, very simple one, a line, y equals x plus 3. I'm going to go ahead and sketch this from 0 to 4, 1, 2, 3, and 4. And if I graph it, we're starting at a height of 3, and we're ending at a height of 7. Now this one's really nice because it's just a linear function right there. And the whole idea of what we're going to be doing here with integral calculus is to be able to find the area under a curve. Now in this situation right here, it is very easy to do, because if I kind of drop a little perpendicular here, if I shade in this area, we should recognize it's a trapezoid. And I can find the area of a trapezoid very easily. It's 1/2 the sum of your bases times the height. Now remember from geometry, the bases are the parts that are parallel to each other, which means this distance down here is our height. So if I plug in all of those numbers, 1/2, the base 1 is 3, base 2 is 7, and our height is 4. Oops, 4. There we go. So when I calculate this, we get, what's that? 2 times 10, or 20. So the area underneath here is 20. Now, that's a pretty simple one. But what if we had a problem like number 2 here? If I want to estimate the area underneath the parabola x squared plus 3 on the same domain. Well, if we sketch this out just like we just did, from 0 to 4, now the difference is I'm still going to start off at a height of 3. But where do I end? I'm going to end up way up here at 19. And now that's not the only problem, because whereas number 1 was a straight line, this line curves like so. So if I drop my perpendicular down here at the 4, I don't have a single formula that can really give me this area. It's not like a line where I can use a trapezoid or a straight line where I can make a rectangle. So the question is, how do we find this area, or how do we approximate this area? Well, that's where Riemann came in. And simply what Riemann said to do was, if you want to estimate the area, we use Riemann sums. And he said, 1, you're going to partition the graph into equal intervals. So you're going to partition the domain. Okay? And we're going to call those partitions delta x. Now for simplicity, what we're going to do down here, we're going to let delta x equal 1. 2, you're going to make rectangles. Now, you're going to make rectangles. Now what that means is between 0 and 1, we're going to make a rectangle. Between 1 and 2, we're going to make a rectangle. Between 2 and 3, we're going to make a rectangle. Between 3 and 4, we're going to make a rectangle. Now, I know these don't look like rectangles yet, but we'll get to that in just a second. Now, after we make rectangles, we're going to find the area of all the rectangles. And then we're going to add them all together. Sum them all together. Okay? And this is what we call a Riemann sum. So now the question is, how do we make the rectangles? So that's what we're going to talk about next. To make the rectangles, we're going to have 2 different types of rectangles that we're going to discuss in here. For now, there's actually 3. We're going to have what's called a right-hand sum. Now, what a right-hand sum basically says, in our first partition, I'm going to pick the number on the right. And if I raise up a hand, the one makes it right, it's going to be at the 1. So what that means is, I'm going to find the height of our parabola at 1. And I'm going to find that area of that rectangle. So how do we write this? Well, to get area, it's the length of the bottom. So it says delta x. So to get my area, it says delta x. I'm going to keep it simple for right now. Times the height of the function. Well, what's the height of the function? Well, that's just f of 1. So basically, simplistically, it's delta x f of x. Or in other words, f of x delta x. That's how you find the area of just one rectangle. The value of the function times its width on the bottom. This should look familiar. It is our differential. So when I find the area for the first rectangle, well, the value at 1, I'm just going to write this as f of 1 times, what's delta x? 1. Then for the second rectangle, between 1 and 2, pick the one on the right, I'm going to pick the 2. And we get a function here. Its value is f of 2. It's still delta x wide, so just 1. Then my next rectangle, from 2 to 3, I'm at 3. Find out its area, and that's going to be plus f of 3 times 1. And then the last one, between 3 and 4, we pick the 4. Now, if you notice, this is going to be an overestimate because we have a lot of shaded little area. That's going to become f of 4 times 1. And then I just plug in everything, ready? The value. Now, if you notice they all have a 1 in common, I can factor out the 1. And I'm just looking at the values. What's f of 1? Plug it into the function. I get 4. F of 2, that becomes, what's that? 4. That becomes 7. F of 3 is 12. And f of 4 is 19. And I'm just going to add those all up together and multiply by 1. That's 11 plus 12 is 23 plus 19. Oh no, I forget what 23 and 19 is, so it's okay. Go off to the side here. 2, carry the 1, 42. So it's 42 units squared. So that's an approximation that it's going to be 42 units squared. Now that's a right-hand sum. Let's take a look at what we call the left-hand sum. Now, to get the left-hand sum, it's the same thing. So if I'm going to graph it out again, just like we just did, between 0 and 4, 1, 2, 3, 4. I'm still starting at 3, and I'm still going to end at 19. But this time, when we partition it, in my rectangles, there's a rectangles. This time we're going to pick the number on the left. So to get the area, it's still going to be delta x equals 1 wide. But now I'm going to pick this height, which is going to be the value at 0. So the formula is still the same. F of x delta x. I'm going to find the area of each rectangle. So for the first one, picking the one on the left, there we go. There's our area. To get the area, it's going to be the value at 0 times my delta x, which is 1. The next one, if I break it up again, it's going to be the value at 1. So f of 1 times 1. And then keep going, and I'm going to try changing my pen. We get f of 2 times 1. And then the last one, the left side, we're going to get f of 3 times 1 also. And I'm going to find those areas. Pull out the 1. 0, we're at 3. Remember my function is this, y equals x squared plus 3. At 1, we're at 4. At 2, we're at 7. And at 3, we're at 12. And I just multiply and add them all together. There's, what's that, 7, and 7 is 14. I get 26 units squared. And if you notice, this one is going to be way of an underestimate. And we can get more accurate by making delta x smaller. What if I partition this into 8 units instead of just 4, right? I can make my delta x even smaller, get me more accurate. So that's what we call the left and right hand sum. Okay, and if you come back for the next video, I'm going to take a look at the midpoint and how we determine underestimate and overestimate.